Hello everyone. In the last videos, we have seen how to design the controllers, the compensators, using the frequency response for the proportional and first order controllers. So basically, what we discussed was for the proportional and then first order controllers, which includes lag, lead, PI, and a PD controller. We know how their frequency response look like and how they change the behavior of the whole system. Now, sometimes a single first order controller might not be enough for satisfying the requirements. For example, you need to increase the amplitude at the low frequency, and at the same time you need to inject some positive phase around the crossover frequency. In such cases, you might need to use a second order controller. The standard second order controllers that we are going to discuss would include the lead lag compensator, which is indeed quite similar to a practical PID controller. The difference between the lead lag and the PID controller, the practical PID controller, should be clear for you. In the case of a practical PID controller, there will be a pole of the controller at the origin. But for the lead lag, there will be no pole at the origin, but there will be a pole pretty close to the origin. So with the practical PID, we will increase the type of the system, but with the lead lag, we will not increase the type of the system, but still we will improve the steady state behavior of the system. So let me give you an idea of how the lead lag compensator will be in terms of the frequency response. In terms of the expression for the controller, we will have GC of S in the form of beta times 1 plus, we can say that, here we have TL times S over 1 plus beta times TL times S. This is the lead part. This is the lag part. Sorry, this is the lag part. And then for the lead part, we have 1 plus TDS over 1 plus alpha times TDS. And this is for the lead part. In terms of the parameters that we have here, so beta will be bigger than 1 and alpha will be smaller than 1. And in terms of the location of the pole and zero of the controller, you should already know that all the poles and zeros will be located on the left half plane. For the lag part, we will have a pole close to the origin and the zero nearby. So this will be what we have for the lag part. For the lead part, on the other hand, there will be a zero and a pole far from the zero compared to with respect to the origin. So that's what we have. And then on the other hand, in terms of the frequency response for this system, we will have something similar to this. Since the pole and zero of the lag compensator are closer to the origin, it means that their effect will appear at lower frequencies. For the lag compensator, we will have some value at the beginning in terms of the amplitude, which is basically 20 logarithm of beta. Then the amplitude will decrease. Eventually it will reach 0 dB when frequency goes beyond some value. And then we will see the effect of the lead. When we reach the frequency at which the zero is located, the amplitude will start to increase. And then once we meet the pole, the amplitude will remain the same. the exact value where we have the final value in terms of the amplitude could be obtained easily by taking the limit of amplitude of GC j omega when omega goes towards infinity, and I think that's quite straightforward. So amplitude of GC j omega when omega moves towards infinity. If we do so, we will get beta times 1 over beta times 1 over alpha. So this will be equal to 1 over alpha. And as a result, over here, we'll have minus 20 logarithm of alpha. In terms of the phase, starting with the lag, there will be some negative phase injected to the system at low frequencies. And then eventually it will go towards the 0. And at some point when we reach the 0 of the controller, some positive phase will be injected into the system. At the omega m frequency, we'll have the maximum, and that is here omega m. And therefore, in some range of the frequencies, we will have positive phase injected. In some range of frequencies, negative phase will be injected. You should keep in mind that the negative phase will be injected at very low frequencies usually. And we should have this in order to not have our system being unstable. The positive phase that we have over here will be injected usually around the crossover frequency in order to increase the phase margin. On top of this, we can also have the proportional controller to move the amplitude plot upwards or downwards depending on our needs. So at low frequency, we can increase the amplitude. At high frequency, we can inject some positive phase into our system. The crossover frequency will be increased a little bit. And by introduction of the proportional controller, we can just do final tuning. So this is how the basically how the frequency response of the lead lag compensator would look like. In terms of for the PID controller, for the practical PID controller, there will be a difference in terms of the initial starting. So for the practical PID controller, we'll have minus 20 dB per decade since the beginning. That will be the main difference. And eventually, the frequency response of the two would look similar to each other. And in terms of the phase, we will start from minus 90 and go towards 0 at some point. So this will be the main difference between the practical PID and the lead lag compensator. I have a numerical example for the lead lag compensator. If we have GC of S expressed as 10 times 1 plus 100s over 1 plus 1000s times 1 plus 4s over 1 plus 20s. And you can see that this part is for the lag and this part is for the lead compensator. Then I can show you how the frequency response of this controller would look like. I already have drawn it in MATLAB and I'm going to just bring it here. So you can see that initially we start with 20 decibel. Then the amplitude goes down, it reaches 0. And then it goes up, it moves up and it reaches 14 decibel. In terms of the phase, initially we have 0 degrees and then we have some negative phase, 0 and then some positive phase. So depending on the location of the pole and 0 of the two pieces of the controller, the lead and lag part, the frequency response that you would get might be different than this, but the general shape will be still similar. So again, you can see that with the lead lag or practical PID controller, we can improve the transient behavior around the crossover frequency by injecting some positive phase, and we can improve the steady state behavior by injecting some gain into the system at the low frequencies. In the next video, we'll have an example in which we'll design a second order controller for a given system. And over there, you will get more details on how to design the different parts. Basically, you can, in terms of designing, you can design one part, let's say the lag part, and then design the next part, which is the lead, and then do the adjustments. But the details will be also covered in the next video in the example. That's all for this video. Thank you for watching and see you in the next video.